going to be they're going to be disjoint. And all of these matrices have the same dimension. That is, the number of rows and columns are the same. So let's say here it's just m cross n. So you can have a rank 1 matrix of m cross n dimension, which is, let's say, triple E is going to be 1, 0, and then everything else is 0. Like only this has a, like there's only one non-zero element in the matrix. That thing is going to have rank 1. And you keep adding ones to the diagonal, you can increase the rank, but keep the dimension the same. So dimensions and rank are different things. It's just important to remember. And so what this is saying is that in the space of Rmn, like in that Euclidean space, you consider these subspaces of matrices of different ranks, then what will be when you minimize, like when you find the closest rank K matrix to A in the spectral norm, the distance of that, so first of all, that matrix is going to be equal to AK, where AK is defined as this, and the distance is going to be the spectral value, sigma K plus 1. So essentially, like what it's saying is the spectral singular values give you the distance between a matrix and the space of matrices of a certain rank. So is like this statement sort of clear now? So what it's saying is, amongst all the matrices of a certain rank, this matrix is going to be the closest to A, and the distance of this matrix to A is going to be sigma K. And this is similar to what Raman's theorem said, but only it was using a different norm, Frobenius norm, and I think probably AKs were different. It was like technicalities were different, but the intuition or the spirit was the same. Now I haven't covered the proof, but like is the statement of the theorem clear? If this was true, then what I said would be the consequence of it.
Sigma K plus 1 is just the K plus 1.
It's the K plus 1 singular value. Yes.
Of A.
Yes. And we have defined AKs to be like a series, or like it's a partial sum, like you keep adding. So you can see that it is a summation of the first K, I don't know what I should call it. So like the left singular vector multiplied with the right singular vector with the singular value. So yeah.
U and V are.
Oh yeah. So let me just.
They are orthogonal.
Yes. Yes.
Sorry, what was sigma K plus 1?
So okay. So let me just write down. So, like this is the SPD decomposition. What this says is that on the left hand side, you have a complete orthonormal basis for M cross M space. That's it. These are, so here's what its shape is going to look like. this is going to be a matrix which is m cross n. M rows and n columns. This is going to be a matrix which is m cross n, but only, and it's going to be diagonal, but only r of its diagonal values are going to be non-zero, where r is obviously going to be less than either of m and n, less than or equal. And then you have n cross n. So this is a matrix which is orthogonal, and b1, b2, and bn. So these are all vectors. And orthogonality just means that if you multiply this vector, this matrix with itself, you will have identity. And I think these are orthonormal, but I'm forgetting the technical difference, like what's the exact difference between orthonormal and orthonormal. I think it just means that these are spanning the entire basis. Orthogonal just means there might be two of them. Like if you take only two columns, then they are orthogonal. They are still orthogonal, but they're not orthonormal because they're not spanning the whole space. I think that's the difference. But anyway, so since this is diagonal, like if you actually do like the algebra of it, you will see that A can exactly be written as sigma I ui bi transpose. A is exactly equal to this. It is the summation of sigma I ui bi transpose. No, all of these are columns. I'm sorry? Wait one second, let me just take this one. I'm right here.
I think you have to pull it forward backwards. Inside of the other.
No, go ahead, come.
Pull it further down. It doesn't go down further.
I don't want to break it. I don't know.
Do you have some switch or something?
No, it's, I think I pulled it down. So, okay,
you don't need
just,
to move.
there's a transpose over there. Yeah, I tried the exact same thing.
Yeah. There's
I mean, so, let me make it smaller. E1, B2, En. There's a transpose outside. Yeah, so basically all of these are columns. So all of these things are columns. And so when you multiply this column with this column, it's going to be a matrix. So all of these summations are well defined. Everything that you can actually sum out with. And what this what this is saying is if you take only the first k of these, where k is less than r, and you take their sum, and you sum them up, you will see that this is going to be the matrix that you get, and it's going to be rank k, and that is easy to see because it is essentially it is a multiplication of just the k columns here and k over there, and therefore it has only k singular values, and therefore it is of rank k. Like I can go over why it is rank k even more. But yeah, I mean, so this is going to be this is what the statement is saying. Let me know if there are more doubts. So just about the statement of the theorem, what is this theorem even trying to say? So here what was the original question? Yeah.
Probably not the original question, but you mean to say that AK is, for example, you are writing U into a diagonal matrix into V transpose. Do you mean to say that AK has K non-zero diagonal elements and A has more than K non-zero diagonal elements?
Yes. So AK is just like if you take K of these.
So it means you can write A as A equal to sigma I plus 1 to T plus something. Sigma
A will be equal to I equal to 1 to R.
1 to R.
Yeah.
So I mean, it's
Exactly equal to
it's like a tensor product of U and V and multiplied with the spectral.
I shouldn't say tensor product, like it's just outer, like it's just U into V, like it's just matrix product, right? Like I don't know what you mean to say, because these are all vectors, right?
So like any matrix can be written as tensor product or outer product of two vectors and summed over with the weights of the spectral mass.
Okay. So yeah, so as like these are vectors, and then when you multiply a vector with a row, you get the outer product, which you can say is the tensor product. But yeah, I mean, I don't want to like introduce more words like names. And this is the SVD, this is the singular variable composition. But I remember like I might not have answered the original question.
I think I figured it out when I realized it was K less than R, and then so it would just be the next singular value.
Yeah, it's just So you have K over here and just the next singular value, and there will always be a next because K is less than R.
Is similar to eigenvalue decomposition. Would it be that it would be the next largest? Can you just assume like, oh, I can just assume they're ordered in this way? And
So here's the thing. Eigenvalue decomposition only exists for square matrices.
but I guess one of the properties is
When he's asking about whether they are ordered.
Oh yeah, these are ordered. So like you have the biggest one on the left.
okay. So you can just arrange them without loss of generality, however you wish.
And also they are always positive. Singular values are always positive, and eigenvalues may not be.
So why is this true? Because I was thinking that would be the sum of all the smaller eigenvalues. So I don't know if I'm thinking about it correctly.
This will be the
Why
sum
would it
of
be the
all
next
of them?
smallest? Yeah,
Not the biggest one.
not the sum of all the smallest eigenvalues. Is what I thought it was. Something
Yeah.
like that.
What you're saying is it should be sigma k plus 1 to R, basically.
Yeah.
That's
something.
what it intuitively should be. Right, okay. But I mean, it's not, and it has to do with like, so what do you think? So, okay, so are we clear about the definitions of all the norms here? Like, what is the spectral norm? Like, I think Raman went over it yesterday.
So along that, the spectral norm is sort of like a max, or a max norm rather than, yeah.
Okay.
So, by definition, and then so basically, and this is like going to be the last thing. By definition, the spectral norm of a matrix is the supremum of, and this is well defined because this is a vector. A is a matrix, and X is a vector, and A into X will be a vector, and so we all know what this is. So it is the Euclidean norm of A multiplied with X.
Is it,
X transpose.
is it the supremum over X, or?
Supreme,
Okay.
for all, over all X such that equals to 1. So over this circle, you find any X, you multiply any X that lies on this circle with AX, find the norm of that, and then whatever the supremum of that is. Supremum is the spectral, like is the L2 norm. That's the definition. And it turns out that if you solve this, such that, then you can get that it's going to be the highest eigenvalue. It's the largest eigenvalue, sigma 1, and there are ways to derive it, I think, but there's also intuition. So I think I'm going to go over like how do you derive this using Lagrange multiplier and over the intuition of why this should be So the equation really is that if your x1 is aligned, so you know that eigenvectors preserve direction. Like you know that A times the eigenvector E1 is equal to lambda 1 times E1. So if x is going to be aligned perfectly to E1, then your output is going to be the maximum. Otherwise, x is going to have some components which lie along E1, some which lie orthogonal to E1. And what will happen is your output is going to be lambda 1 times x dot E1, like inner product, plus lambda 2 times x dot E2, so on and so forth. So if you want to maximize this, since this number is the highest, just put more weight along this E1. Like that's like the equation like that. When you multiply, when you take the when you use this as a function to project it, there are some some principal dimensions, and they have like a nice property that you can, if you break this vector as on that basis, you can easily figure out what the scaling is going to be. And if you there is going to be one dimension which will scale the most, and you put more weight on that direction, and you will get the most output. That's the basic idea. But you can actually, I think, derive it by using Lagrange multiplier also. So you just put in, I have to maximize this plus lambda x minus 1, and then you say what this is, x transpose ax plus lambda times x transpose x minus 1, and then you take derivative with respect to x. I think you will get 2a plus 2 lambda x minus equals to 0, and so you get the fact that x is going to be an eigenvector, and once you know it's going to be an eigenvector, then you know that it has to be one of the eigenvector. Therefore, you can get the norm. There's some more things, but Lagrange multiplier is pretty simple. You just add Lagrange parameters and then take the derivative. I hope everyone had seen at least some form of Lagrange multiplier, maximization. If not, then I can go over that in the next class more. And specifically, we didn't have time to cover Raman's rules. I think we can go over this. But yeah, that's it. So yeah, you can give me feedback on Piazza or personally.
Could I ask you about the notation on what this is?
Yeah, sure. I mean, it's just so the reason why it's bad is because I don't want to knock it everything. Right?
There's actually there's probably
It's not from the video level. It's actually from, so in the document that I made out, there are links